Greetings all. Let's take another look at a second problem involving arc length. So in this problem, what we're given is that the derivative of a curve is given by the expression 3 cosine t minus 2 sine t and 1/5. And we want to find the arc length of the original curve on the interval from minus pi to 13 pi over 6. Now if we go back to our arc length form, our ds is going to be the square root of dx squared plus dy squared plus dz squared, and kind of if we plug in our derivatives of our component functions, then this thing becomes dx squared dt, or dx dt squared, dy dt squared plus dz dt squared dt. So that becomes our form. Now, if we kind of look at this a little bit closer, what we kind of see there is that the dx dt, dy dt, and dz dt, this is really just the derivative of our curve, and so this is really nothing more than the length of the derivative vector for our curve. And so what this really just kind of simplifies to is the norm of v prime dt. And so what we want to do then is to find the arc length for that. Well, that's just the s is equal to the integral over our curve for ds, and kind of doing this with respect to our parameterization becomes a minus pi up to 13 pi over 6 of the length of v prime that we were given originally. So if we kind of plug everything in there, what we get is the integral from negative pi up to 13 pi over 6 of 9 cosine squared plus 4 sine squared plus 1 over 25 underneath the square root. And so what we want to do to kind of simplify that, we take our 9 cosine squared, we split it apart into a 4 cosine squared and a 5 cosine squared, so that we can combine our 4 cosine squared with our 4 sine squared to give us a 4. We have our 1 over 25 left over plus 5 cosine squared underneath the radical dt. So we combine the 4 and the 1 over 25 to get a 1 over 25 plus 4 cosine squared. So still not incredibly nice to deal with, but if we kind of transform it just a little bit more, what we see is that if we plug in our 1 minus sine squared for our cosine squared, distribute that 5, and then combine the constants together, we end up with an expression of 226 over 25 minus 5 sine squared. Now, kind of the last step that we want to do for this is to factor out this 226 over 25 from underneath the radical. So if we do that, we get a square root of 226 over 5 on the outside, and then we get the square root of 1 minus 1 over 25 times 125 over 226 times sine squared. Now this doesn't really look like we've gained anywhere, but this introduces a brand new class of integrals that we really haven't seen before. And in particular, those guys are called incomplete elliptic integrals of the second kind. Now they are really of the form 0, the integral from 0 up to phi of the square root of 1 minus k squared sine squared d phi. Now when you really run into these, typically kind of how they were first discovered was that people were taking the arc length of ellipses, and that's kind of where this elliptic part comes in. They were doing the arc length of an ellipse, and so what they found out was that these things are not usually expressible in terms of elementary functions. And so that kind of messes things up. We can't really integrate them. None of our tricks tend to work. And so we just kind of have to leave them in this form. If we want to kind of evaluate those, then it becomes more of a numerical process to let us do that. And so the notation that you generally see for these things, this capital E of phi k, the phi and the k really being two parameters, phi being the upper limit on the integral, and k being the constant squared that's multiplying the sine squared inside or under the radical. And so if we kind of go back to our original curve, Then we've got this arc length being the square root of 226 over 5 for this thing. Well, we can split this integral up into an integral from negative pi up to 0 and an integral from 0 up to 13 pi over 6. If we then do a u substitution on this first one and say, well, if u is negative t, du becomes negative dt, plug that thing in, we've got a negative sine squared u on the inside, but that square kills that off that negative from the inside, so that one goes away. Then we've got this negative on the outside from our du, and then if we switch the order of integration, so we go from 0 up to pi, it takes care of that negative, and so we get an expression of the form square root of 226 over 5 times the integral 0 up to pi of the square root of 1 minus 125 over 226 sine squared. So now this thing looks like an elliptic integral. Our second one looked like an elliptic integral to begin with, so that was just our e of 13 pi over 6, square root of 125 over 226 for the constant. And so now for that first one, we can write that one also as an elliptic integral, square root of 226 over 5 times the elliptic elliptic integral of the second kind, evaluated at pi and root 125 over 226. And so if we evaluate those numerically, what did we do with those? We really just plugged those things into Wolfram alpha to give us some kind of numerical answer. So for the first one, we get 7.95807. For the second one, 17.4519. Put those together and we get 45.40997. So this, and kind of the importance of this one is there to introduce this new class of elliptic integrals, things that we would see kind of typically in these situations when we are dealing with arc length. So I hope this has helped you out a little bit, and I hope to see you guys at the next homework problem. See y'all later.